Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Last time we completed the LightSet class, which now supports point lights and spotlights. And today we are going to connect the platform-independent light functions to the low-level LightSet member functions. We are also going to test if we can add callable lights in Test Renderer, and finally we are going to update the GPU light buffers to handle callable lights as well. Today we'll start by adding a couple of new functions that will connect the platform-independent light property setters and getters to their platform-specific counterparts. First, we need to add the new parameter types to the light parameter enumeration. These are attenuation, range, umbra, and penumbra. Then we can write our setter and getter connection functions, starting with set attenuation. Next one is set range. Note that whenever there is a call to vector size function, we are using a constexpr macro to keep things compatible with standard vector. Please watch this video if you'd like to know what that's all about. The last two setters are for umbra and penumbra. We continue with the getter functions. In the same order, we start with attenuation, followed by range, umbra, and penumbra. Now we can add pointers to these new functions to the arrays of set function and get function pointers. We need to implement the member functions of the platform-independent light class, which we'll call the set parameter and get parameter functions. These are again the attenuation, range, and the cone angles. Here we don't have separate functions for umbra and penumbra, so we call set parameter twice in order to set both cone angles. The getter functions work in the same way, except they call get parameter and return a value. Here we do have a separate function for umbra and penumbra angles. I believe that's all we need to do to add point lights and spotlights and to change their various properties. Let's write a bit of code to test what we have been doing so far. Here we have a function that creates a few directional lights. I'd like to add a section here that creates as many callable lights as we want. First, I'll write a function that creates a light given its position, direction, and type, which will then be added to the light set with the provided key. We create a game entity to which we can attach the new light. In order to make random lights, I need a function that returns a random number between 0 and 1. We can use the pseudo-random number generator from C library for this. It returns a number between 0 and rand max. So if we divide this value by rand max, we get a number between 0 and 1. We can also give our function an optional parameter that can be used as the minimum. For example, we can use this to define random colors for our lights with a minimum RGB value of 0.2. I would also like to be able to toggle between randomly generated lights and a few lights that I place manually in order to make it easier to inspect them. That's why we have this random lights macro here. We can use this to create lights with random ranges and cone angles. However, when we set this macro to 0, light properties are set to specific values. After filling the light init info, we can use it to create a light and add it to the lights array. In case we don't want random lights, I create 3 point lights and 1 spotlight and place them somewhere near the center of our scene. If we want to create lots of random lights, we first set the random seed. Here I use a constant value because I'd like to create exactly the same set of lights every time that I run the application. This is because when we have artifacts because of bugs, we can go back and check the same lights to see if the issue was fixed. This would be harder if the lights keep changing. We'll create our lights in a rectangular volume, which we can scale to fill the room. We also have a dimension which we can use to define the number of lights. Using the dimension, We can loop in X, Y, and Z directions and create random lights for each light set. Note that we start at 0 in the Y direction because we don't want to create lights under the floor of our scene. We use a random orientation for our spotlights. In addition, roughly half of our lights will be spotlights and the other half will be point lights. Let's run the application with just 4 callable lights. Of course, we are not using them to light anything yet, so we can't really know if everything's working as intended, but at least it doesn't crash. Now let's take it a bit further and create 1,000 lights per light set. Well, it's still able to run, which is great. Of course, we could set some breakpoints and inspect our data, but what's the fun in that, right? Something that we can already test visually is switching between light sets. We have directional lights in both light sets, so I can easily create a counter and use it to toggle between them. Although I'm glad that it works, I'm not really happy about the colors. Let's make it more pink. Yeah, pink and purple. I like. Great, now we need to update the D3D12 light buffer class so that we can send the callable light data to the GPU. When we created this class for directional lights, which we did in this video, I already added the 2 enumerations for callable lights and calling info. Today we need to actually create those buffers and keep them up to date with the data from the current light set. This happens in update light buffers function, where we copy data from the light set and resize our buffers if necessary. For callable lights, we only copy the data if there was a change in any of the light properties, or if we are using a different light set from the previous frame. In this video, I'm going to write how this is done functionality-wise, and we'll clean it up and optimize it a bit in a later video. First, we calculate the needed size for callable light buffers, and we get the current buffer sizes. The code for resizing and updating directional lights remains the same. We need to add new code for callable lights. If the buffer size that's needed for the light data is larger than the current buffer size, we need to resize our buffers. When this happens, we need to copy the entire light data and we set a Boolean flag to indicate that buffers were resized. As I mentioned, we also copy the light data if we are using a different light set, so if buffers were resized or the light set is not the same, then we are going to copy the entire light data buffer. To do this, we need access to the guts of our lightset class. We could write accessor functions for this, but there is no one except the light buffer class who would or should have access to lightset data. So we just make the D3D12 light buffer class a friend of lightset class. Now we can copy each buffer from lightset to our GPU buffers. We also update the lightset key in case it was changed. When we copy all buffers entirely, we are actually done and we can exit this function. Again, we set a Boolean flag to indicate this. However, if we didn't copy everything, we need to look at every light to see if it was updated and copy its data if necessary. If all lights were updated, it doesn't matter if any dirty bits flag is set, and we just clear all flags for the current frame index. This may be a good time to explain dirty bits flag. We keep the data for each light in a few arrays that belong to the lightset class. This data is then copied 3 times to GPU accessible memory. This is because we have 3 frame buffers. This basically forms a small ring buffer with 3 elements, with each element being an instance of D3D12 light buffer. Whenever we modify a light property, we save that change in the lightset class first, but we need to also communicate it to the GPU. That means that whichever frame buffer we are at when there was a change, we need to copy that change to the light buffer that's going to be used for the current frame. So to keep track of which buffers have been updated and which ones still need to be updated, we set as many bits in dirty bits flags as we have frame buffers, which in our case is 3. Then every time a buffer is updated, we clear the corresponding bit. After all bits have been cleared, we are done updating the buffers until something changes in the lightset class again. If not all buffers are updated, we need to look at each light and copy its data if it was changed. We do this by looking at each light's dirty bits flag and checking if the bit for the current frame is set. If that's the case, we copy the light data. First, we assert that the light data are within the range of our buffers. Next, we compute the address where we need to write the light data to each buffer. We copy one element from each array to our buffers. At the end, we clear the dirty bits flag for the current frame index. This is all for updating light data. Now we need accessor functions that return the GPU virtual address to each buffer. I'll do a quick check to see if I didn't mix up any enumerations. Here I made a copy-paste error. Other than that, everything looks okay to me. I do recommend setting breakpoints and checking the paths that are taken for each different condition, such as alternating light sets and light data updates. This concludes the episode about adding and managing callable light data. In the next episode, we'll look at how we can use our lights for rendering. For this to be practical, we need to only use lights that affect each pixel, and that means that we need to call all other lights that don't. So the next episode will be all about light calling and rendering with point lights and spotlights. If you haven't done already, make sure you subscribe and ring the bell to get notified when the next videos come out. As always, thank you so much for joining me, and I hope to see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!